Last day, I think we discussed about excess pressure inside a air bubble. Right now, if air bubble is trapped inside a liquid, so then we derive an expression for excess pressure. We derive an expression for the excess pressure. The P1 is the pressure of the liquid, then P2 means pressure inside the air bubble. Then I told you that pressure inside the bubble is always larger than the pressure outside the bubble. Then we obtained that pressure difference, the P2 minus P1 in terms of surface tension and the radius of the air bubble. P2 minus P1 equals 2TO simple R. Right? That equation is very important when you do questions. Therefore, learn by heart that equation. That's important. Now, how we derive the equation? That excess pressure P2 minus P1, if from delta P equals 2TO simple R, how we derive the equation? I considered air bubble trapped inside liquid, and I considered half of the air bubble. The reason why I took half of the air bubble and why I derived the equation, the reason is, suppose if I take the full air bubble, resultant force acting on the air bubble due to the liquid pressure P1 is 0. Very similar way, if I try to find the resultant force acting inside the air bubble due to the pressure of P2, that is also 0. So that's why I have considered half the air bubble and I did the equation. Right? Now, suppose rather than an air bubble trapped inside liquid, suppose if there is a, let's say, a soap bubble. Now, I think you know what is soap bubbles. What can you say about the difference between air bubble trapped inside a liquid and a soap bubble? Generally, we say that soap bubble has two surfaces. You understand what I'm saying? In here, air bubbles, they have only one surface, but we say soap bubbles have two surfaces. Therefore, if I take half of a soap bubble, it would be appear this way. If I take one soap bubble and if I take the half of the soap bubble, then I will obtain something like this. I'm obtaining something like this. Half the soap bubble. The only difference is, understand soap bubbles have two surfaces. Two surfaces, that's the important. If I consider half of the soap bubble, it is having two surfaces. Right. Then if I mark the forces, the resultant force acting on the soap bubble due to the liquid pressure P1, resultant force will be to the right side direction F1. There is no difference. No matter it's soap bubble or air bubble, resultant force acting on the half of the soap bubble due to the liquid pressure outside is F1 to the right side direction. So very similar manner, the resultant force acting inside the bubble due to the pressure inside the bubble is to the horizontal direction F2. In this case also F2. But the only difference is resultant surface tension force. Now when I was considering air bubble trapped inside a liquid, I considered air bubble has one surface, therefore resultant surface tension force acting on this half of the bubble is 2 phi r simple T. But when it comes to soap bubble, understand soap bubble has two surfaces. Just assume that this gap is very small. So therefore, what is the resultant surface tension force acting on the soap bubble? 2 phi RT into 2. You understand what I'm saying? Soap bubble has two surfaces. if I mark the surface tension forces, now this surface also undergoes surface tension forces, and also this surface also undergoes surface tension forces. If you want to find the resultant surface tension force acting on the soap bubble, it will be 2 phi r into 2 into T. I hope you understand. So then how would be your equation for excess pressure inside the soap bubble? It will be same idea. F1, if you consider the equilibrium of half of the soap bubble, then resultant force acting on the bubble due to the liquid pressure, external pressure is, we know F1. I know F1 equals P1 into phi r square. I hope you guys understood when I was discussing this one. And resultant force acting on this half of the soap bubble due to the inside pressure, that is F2. Right? Then F1 plus 2 phi RT means surface tension force acting on half of an air bubble. Now, if there's soap bubble, resultant surface tension force will be 2 phi RT into 2. Right? So therefore, I can write that F1 plus resultant surface tension force will be 2 phi simple R capital T into 2 equals F2. Then F1 I can write down P1 into phi R squared. 4 phi R simple T equals P2 into phi R squared. Right? So when you simplify this, you will obtain that excess pressure P2 minus P1 will be equal to 4 TO simple R. Excess pressure means delta P. 4 T over simple R. You must learn by heart this equation for a soap bubble. For an air bubble, excess pressure will be delta P equals 2 T over simple R. Now, what is the reason excess pressure in soap bubble is 4 T over simple R rather than 2 T over simple R? The reason is soap bubble has two surfaces. Then write down up to down. Then write down up to here. Run up to here. Right. Then that idea is also done. That idea is also discussed. Okay. Now we'll write a small knot. Give me a second. Now, first of all, draw this diagram now. Previously, there was a complete. Now, first of all, we derived the equation for excess pressure for an air bubble trapped inside a liquid. So then draw that complete air bubble. Radius of the air bubble is simple R. Pressure of the liquid is P1. Pressure inside the bubble is P2. And just consider half of the air bubble and draw these forces after you drew until here. Then start writing what I'm going to say right now. Right. Now write down. Consider spherical air bubble in a liquid and the equilibrium of 1/2 of it. Write down. Consider spherical air bubbles in a liquid and the equilibrium of 1/2 of it. Next point. Let simple r be the radius of the bubble. Comma, capital T, the surface tension of the liquid. Capital T, the surface tension of the liquid. Comma, P1, the pressure inside the bubble. P1, pressure inside the bubble. P2, pressure outside the bubble. Right. After you do these two diagrams, Now, next point, we'll write as a point. The force acted upon the half. The force acted upon the half of the sphere, or half of the bubble, by surface tension equals the force acted upon the half of the air bubble, if not half of the sphere, by surface tension equals 2 phi r into capital T. 2 phi r into capital T. Next point, for next line. The force acted upon curved surface of half of the bubble. The force acted upon the curved surface of half of the bubble by the external pressure. By the external pressure, P2 equals phi r squared into P2. The force acted upon the curved surface of the half of the air bubble by the external pressure P2. By the external pressure, it must be by the external pressure P1, right? P1. If not P, it's P1 equals phi r squared into P1. Next line. The force acted upon the curved surface of the half of the air bubble by the internal pressure P2 equals phi r squared into P2. Then write down considering the equilibrium of half of the air bubble. Considering the equilibrium of half of the air bubble, you see this here. Right. Write down until here and highlight this equation delta P equals 2TO simple r. Highlight the equation. So again, what you do for a soap bubble. Again, write down your topic for a soap bubble. Write down soap bubble has two surfaces. A point after the topic soap bubble has two surfaces, and repeat the same thing. The force acted upon half of the soap bubble by surface tension equals 1. 4 phi r. The remaining 2 points are same, right? Force acted upon the curved surface of the half of the soap bubble by the external pressure, phi r squared into P1. Then the force acted upon the curved surface of the half of the soap bubble by the internal pressure, phi r squared P2. Then derive this equation. Considering the equilibrium of soap bubble, from this diagram, derive this equation. Excess pressure equals 4TO simple r. Excess pressure equals 4TO simple r. Right? Now from this we can obtain an idea. The conclusion is very carefully listen. Very carefully listen. The conclusion is, always understand, if you have a concave, if not convex or flat meniscus, you need to understand the pressure just above the meniscus and pressure just below the meniscus. For an example, just consider a concave meniscus. If I consider concave liquid meniscus, now concave liquid meniscus, summary. Right? Now, concave liquid meniscus. If I draw the corresponding sphere by taking this concave meniscus, that radius of the sphere, we see that radius of the curvature. Okay. The radius of the sphere we see as radius of the curvature. So this radius simple r, we see radius of the curvature. Simple r. Then if I take a point just below the meniscus, point E. If I take a point just above the meniscus, that is point B. If the meniscus is concave, understand always the pressure just above the meniscus is large, pressure just below the meniscus is small. That means pressure at point B is large, right? The pressure at point B is larger than pressure at point A. An important point. If you want to find the excess pressure PB minus PE, if you want to find the excess pressure PB minus PE equals what? 2T over simple r. Am I getting 2T over simple r? If it is for a convex meniscus, convex meniscus. Same 2 points. Let's say this point is point A, point just below the concave meniscus, point A, a point just above the meniscus, point B. Right? Let's understand the point inside the sphere. Also understand the point inside the sphere has the larger pressure. Point inside the sphere always has the largest sphere. Always understand point inside the sphere always has the largest pressure. Now in this case we know that point A is inside the sphere. Pressure at point A must be larger than pressure at point B. In here we know PA must be larger than PB. If you want to find the excess pressure, the change in that pressure, PA is larger, PB is smaller, PA minus PB. PA minus PB equals 2T over simple r. Right? Now, next instant, if there is a flat meniscus, understand if the meniscus is flat, if I take 2 points just below the meniscus and just above the meniscus, they are equal. Pressure at point A and pressure at point B must be equal. Right? Then what can I say about the excess pressure? Excess pressure will be 0. Am I correct? PA minus PB or PB minus P will be 0. So therefore, 0 equals 2T over simple r. R equals 2T over 0. Then radius of curvature will be infinity. The important thing you will note is, suppose if the liquid surface is flat. If the liquid surface is flat, understand radius of curvature will be infinity. That's an important idea. Okay. Then after that knowledge, now put your main topic, variation of radius of curvature. Variation of radius of curvature. And excess pressure of a bulb and excess pressure of a bulb forming at the end of the tube. Forming at the end of the tube. Right now, it's very important. it is evident that from equation delta P equals 2T over simple R and delta P equals 4T over simple R, comma, it is evident that excess pressure increases when radius of curvature decreases. When radius of curvature decreases. Right. Now let's say just think about a tap. When we open the tap, what would happen? The water, initially, when we slowly open the tap, the first drop of that water, just imagine how would be the first drop of water would form in the tap, or in the opening of the tap. Right? When we slowly open the tap, what will happen? Now, slowly, gradually, that water drop will be formed, right? So if I explain that idea properly, now here understand when t equals 0, it's not initially we can now when you gradually open the tap, you would notice that some kind of flat liquid level exactly at the opening of the tap. Right. Then what can you say about the radius of curvature? If we have a flat meniscus, from flat liquid surface, we know radius of curvature will be infinity. Simple R will be infinity. Now I say that capital R means radius of the cross-sectional area of this tube. What is capital R? Write down somewhere is radius of the cross-sectional area of this tube. That is capital R. Then when I slowly open the tap, more I open the tap, what would happen for the liquid meniscus? The shape of the liquid meniscus? Now it's getting little by little curved, right? Now initially we could identify some kind of flat meniscus. If I slowly if I open the tap, I could notice that what would happen to the shape of this meniscus? Now it's getting a little bit curved here, a little bit curved. A meniscus becomes a bit curved one. Bit curved. Then if I complete the corresponding sphere, it's very large one. Right. Large sphere. Then simple R is radius of curvature, right? Simple R is radius of curvature. Simple R is radius of curvature. Now this time radius of curvature will be very larger than the radius of cross-sectional area of the tube. But if I further open the tab, what will happen to the radius of curvature is getting very low. More the meniscus get curved, what would happen to the radius of curvature? Less the radius of curvature. If the meniscus gets curved more, radius of curvature will be also less. Understand? I hope you understand what I'm saying. Now, more I open the tap, what would happen for the shape of the meniscus? Meniscus will get more curved. More it gets curved, its radius of curvature will be less. Radius of curvature will be less, but still the radius of curvature is larger than the radius of cross-section area of the tube. If I complete the like this. Right. Then exactly at a certain instant, what will happen? Radius of curvature would be equal to the radius of cross-section area of the tube. Okay. At a certain instant, what will happen? Radius of curvature will be exactly equal to the radius of the cross-section area of the tube. R equals capital R. If I further open the tab, what will happen? Again, simple R. Radius of the curvature will start increasing. Now, from initial instant to the instant where radius of the curvature equals to cross-sectional radius of the tube. If I further increase, what will happen? Again, radius of curvature will be increased. So that I understand, in this case, the liquid would be like this. Until the liquid drop falls, if I do the graph, the variation of radius of curvature with the time. Variation of radius of curvature with the time. If I draw the graph, variation of radius of curvature with the time. If I draw the graph, it will be very close to something like this. Like in the time is simple to understand. The time is simple to understand. Radius of curvature will be equal to cross-sectional radius. If I do the corresponding x expression, now we know from equation delta p over delta p equals 2t over simple r. What would happen when radius of curvature decreases? Excess pressure would increase. Delta p equals 2t over simple r or 4t over simple r, those equations, we understood that when radius of curvature decreases, excess pressure increases. When radius of curvature increases, excess pressure decreases. Then I explained what will happen for the radius of curvature from here to here. Until radius of curvature equals to cross-sectional area radius of the tube, radius of curvature gradually decreases. Then beyond this, again radius of curvature starts increasing. So there, if I plot the variation of excess pressure, if I plot the variation of excess pressure delta P with the time simple t, with the time simple t, it will be something like this. When the time is simple to understand, excess pressure will be excess pressure means delta P equals 2t or simple r. When the time is simple t, simple r equals capital R. So therefore, your excess pressure will be delta P equals 2t over simple r. Now simple R is capital R. So therefore, 2t over capital R. I hope you understand. Then those two graphs is also important. Right. Okay. Now only the last important theory sections. And if I cover these theory sections, all the theory related to surface tension will be completely discussed. But we want to discuss some questions. We'll discuss another day. Okay? Don't worry. Now capillary rise. Now very carefully listen what's happening here. I'm going to discuss about capillary rise and capillary depression. Okay. If I dip a capillary tube into a liquid, if I dip a capillary tube into a liquid, right? Okay. Capillary rise. Capillary rise. If I dip a capillary tube into a liquid, partially, very carefully. Right. Now we know that generally, just think about a liquid like water. Now I dipped this capillary tube into a liquid like water. Then usually we know that when you consider outside liquid surface, that outside liquid surface would be in this shape. Now you know the reason. Okay. But this time I am not interested with how would be the liquid surface outside the tube. I am interested what would happen to the liquid surface inside the capillary tube. Because capillary tube is inside, there's a hole. As a result, liquid is inside also. Now I am interested with what would happen for the liquid surface inside the tube. And then we know that inside the tube, liquid surface would be inside the tube, liquid surface would be. Now you guys know that inside the liquid surface would be something like this. Am I correct? Right. This would be the liquid surface inside the capillary tube. Now the problem is now, if we dip this capillary tube into a liquid like water, and then we know that then the liquid meniscus inside the capillary tube must be some kind of concave shape, then we think this is correct. But obviously understand this is not correct. The reason is, right, if I consider, okay, the reason is, very carefully see. Let's take about a point now. Okay. Below the concave meniscus, understand that very carefully. This point is very close to the liquid surface. That's the important thing you want to understand, right? Then if I consider a point capital B. The point capital B means this point B located on the surface of the liquid. Then what can we say about the pressure at point B? We know pressure at point B exactly equal to atmospheric pressure phi. I say atmospheric pressure is P. We know atmospheric pressure is P naught. Then obviously we can say this point B is exactly at the surface of the liquid. And then we know that pressure at point B, PB equals, we know that P naught. PB equals P naught. And also understand now it seems like this point A is much below than point B. It's wrong. Understand this point A means just below the concave meniscus. So therefore you should understand point A and point B are at the same horizontal level. Always understand this point A and point B both are at same horizontal level. Point A and point B both are at same horizontal level. Understand that one. Okay. If I take a point just above the concave meniscus, C, what can you say about the pressure at point C? We know pressure at point C exactly equal to atmospheric pressure. We know PC exactly equal to atmospheric pressure P naught. Right? Okay. Now, this is my equation 1. Equation 1, this will be my equation 2. Okay. Now, what can we say about the pressure at point A and pressure at point B? Now, pressure at point B equals atmospheric pressure. If I write down pressure at point A, very careful now, understand point A and point B are at the same horizontal level. point A and point B both are the same horizontal level, then we know pressure at point A must be equal to pressure at point B. Okay. Now, in case you have to understand, in case now the problem what I'm doing, I'm checking with the what I told you to draw the liquid, the how the liquid would appear inside the capital tube, right? So then now still I have no idea what would be the shape of the liquid meniscus inside the capital tube. Now I'm studying. Then now this point A and point B are the same horizontal level. Then we know in hydrostatic we learned that same liquid, same horizontal level, pressure must be equal. PA must be equal to PB, right? That's important idea. If these 2 points are the same level, but you have to understand, if these 2 points are the same level, PA must be equal to PB. If these 2 points are the same level, you know PA must be equal to PB, right? But I can write down PA in terms of P naught, surface tension capital T, radius of curve is simple R. Excess pressure, we know that excess pressure in this case, excess pressure, I can write down excess pressure as PC minus PE. PC minus PE equals how much? PC minus PE equals 2TO simple R. 2TO simple R. Then I can write down pressure at point A equals PA equals PC minus 2TO simple R. PC minus 2TO simple R. That means pressure at point A equals PC means P naught minus 2TO simple R. Now only problem begins. Right? Suppose point A and point B are at the same liquid level. Suppose if the point A and point B are at the same horizontal level, we know that pressure at point A and point B must be equal. But we know pressure at point B is obviously atmospheric pressure P naught. And now I exactly found pressure at point A. Pressure at point A is equal to how much? P naught minus 2TO simple R. And now we can understand PA and PB are not equal. Right? Now, initially I also thought that A and B both points are the same horizontal level. But when I found the pressures on there, I realized that PA and P2 are not equal. That means understand A and B should not at the same horizontal level. Then what would happen? This liquid meniscus would be somewhat elevated. So what happened? This liquid meniscus should be rising. Okay. So therefore, understand this is contradiction because this can't be. This can't be. So therefore, if I draw the right liquid, this liquid meniscus would be rising somewhat. Okay, rising. Now I am taking same point. This point is point B. This point is point A. Okay, this point is point A. Okay. Now this point I say point C. This point will say point D or something else. Okay, this point D. The height of the liquid in the capital tube is simple H. Simple H. In this case, very carefully listen. So now I see this is my point. If I this is my point E now. Now PC is same now. You know, PC is exactly equal to atmospheric pressure. PB also exactly equal to atmospheric pressure. So PC and PB both should be equal to atmospheric pressure. You know, PC equals PB must be equal to atmospheric pressure P naught. This is my equation 1. Now, how can I find the pressure at point A? Pressure at point A means we know that, like we discussed previously, we know that excess pressure delta P equals 2TO simple R. Then I can write down pressure at point A equals, as we discussed, P naught minus 2TO simple R. P naught minus 2T over simple R. Equation. If I ask you to write an expression for pressure at point D, pressure at point B, total pressure at point D, in terms of PA and H, density of the liquid rho and G. You will write that. If I ask you to write an expression for pressure at point D, in terms of pressure at point A, H, rho, G, you write down that. If you can this liquid column, you write down PD equals H rho G plus PE. Equation. Am I correct? And also we know that PD, point D and point B are the same horizontal level. So therefore we know PD equals PB. We know PD equals PB. Then from these four equations I can write down PD equals PB. If PD equals PB, PB means P naught. These four equations I can write down 1, 2, 3, and 4. I can write down. Now. PD equals P. PB equals P naught. Therefore, I write down this one. From equation 3, I write down PD for P naught. P naught equals H rho G. P A means what? P naught minus 2T simple R. Then P naught cancel out. I can write down 2T over simple R equals H rho G. Do you understand? So H rho G equals 2T over simple R. This is also somewhat important equation. Please learn by this equation also. 2T over simple R. If you want to find the rise of the liquid inside the capillary tube, the rise of the liquid inside the capillary tube is simple H. Density of the liquid is rho. Gravitational acceleration is G. Surface tension of the liquid E, and radius of curvature R. Now, mostly they ask you to find a simple H, but the problem is we can the density of liquid, right? Gravitational acceleration obviously 9.8, if not 10 ms minus 2. Surface tension of that liquid also we can find by there are some catalogs. Then we can go through those catalogs and we can find surface tension of liquid. The problem is radius of curvature. Radius of curvature means the curveness. And if I draw a complete sphere, the radius of that sphere, radius of curvature, understand we can't measure. Now the problem in this equation is usually they ask us to find simple H, right? The problem in this equation is we don't know radius of curvature, and we have no idea of measuring the radius of curvature of the liquid also. It's not easy as you think. So therefore, understand what we do. We try to write down this radius of curvature in terms of cross-sectional area of the tube. Sorry, we write radius of curvature in terms of radius of cross-sectional area of the tube. That means I'm writing simple R in terms of capital R. So write until here, then I will show that how to write simple R in terms of capital R. Then how do we alter this equation H rho G to T over R including that capital R. Now write until here. After you wrote until here, put your topic that relationship between tube radius and meniscus radius. That is relationship between tube radius and radius of curvature. Right. Now, if I complete this radius, Now, understand now in here now, what's my goal? The problem is I want to remove the simple r and I want to write down the simple r in terms of capital R. How do we draw that? That's my liquid. That's my liquid. Well, if I draw a tangent, line to the surface which runs a solid, this tangent line, right? This tangent line. This angle measured from the solid to the tangent line to the liquids we named as angle of contact. Angle of contact. Then understand this is the same thing. Okay, the same thing. If I draw a line, this line is perpendicular. This line is perpendicular to the tangent line. This line is perpendicular to the tangent line. Then this is simple radius of curvature. This will be okay. This will be your capital R. Your capital R. This angle is theta, 90 minus theta. Then I can say that this right angle triangle, I can say that theta r capital R. I can say that r cos theta. R cos theta equals capital R. Therefore, R equals capital R over cos theta. This is the important equation. Now I wrote simple R into capital R. Then if I substitute this equation, I can write down h rho g equals 2t over simple R means capital R over cos theta. That means something like this. Right? Learn by this equation. These are important. I hope you guys understood how I write this. Likewise, you want to learn this capillary depression also. Now put your main topic capillary depression. Mostly that is for liquid like mercury. Capillary depression. Now, if I explain that also, now in capillary depression, understand what's happening. If I take a point just below the meniscus, now it's a convex meniscus. Convex meniscus, we know pressure at point B is P naught. Then if I measure pressure at point A, this is point C. If I measure pressure at point A, understand P minus PC, right? PA minus PC. If I measure pressure at point A, will be understand P naught plus 2Q simple R. But if A and B are at the same horizontal level, their pressure must be equal. But we can clearly see that pressure at point B is P naught, pressure at point A means P plus 2Q simple R, right? But as a result, now this can't be accepted. So therefore, liquid meniscus should be gone down. Okay. So liquid meniscus should be gone down. If I draw that diagram, right? Now, it's how a liquid would be. Then if I take 2 points, now this point and this level. This is a simple H. Pressure at this point is we know it's P naught. If this point is point B, this point is point A. Then we know PA equals P naught plus 2TO simple R. So I can write on PB as what? PB equals H rho G. PB equals H rho G plus P naught. Then, right? Then that must be equal to PA. The PA means we know that P naught plus 2T over simple R. H rho G plus P naught. Then here P naught will cancel out, and I'm getting that again same equation. H rho G equals 2TO simple R. 2TO simple R. Now again, you will write down the simple R in terms of the capital R. In that case, what would you do? Now again, here is what you want to write down simple R in terms of capital R. In that case, what will you do? For the diagram again. Okay. If I do the diagram again. If I draw it. In this case, if I do the diagram, without it. Without you. And if you do the tangent, if I do the tangent will be like this. Okay, I'll draw a big diagram, then you'll understand. Then if I draw a tangent, it's my tangent. If I measure the angle, this is my angle theta. I define this angle as alpha. Angle of contact is theta. I define this angle as alpha. So then, if I draw, this is the center of the sphere. This is perpendicular. This is perpendicular. Then, if I this right angle triangle, understand right angle triangle. This is simple R. Distance from the point O to this point is simple R. This is radius capital R. Radius to the tip capital R. Then you will understand alpha 90 minus alpha, this angle will be alpha. Then you get that R cos, if I this right angle triangle, you will understand that alpha R capital R, you get that R cos alpha equals capital R. Then you will get that simple R equals capital R over cos alpha. Then the equation will be H rho G equals 2T cos alpha over what? Capital R. Understand what can I say about this alpha and theta? Alpha equals 180 minus theta. So therefore cos alpha means, understand, cos 180 minus theta. If not minus cos theta equals cos alpha. Remember this also. So then that idea is also discussed. Right. So then almost everything is simply explained. Right. Okay. Now one more theory part there. Now surface, put your topic, surface tension force acting on an object deep in the liquid. Write down, put a topic, surface tension force acting on an object deep in the liquid. So now looking. Now we understood what is capillary rise and capillary depression. We understood. Now put your topic, surface tension force acting on an object deep in a liquid. Acting on object deep in a liquid. Now let's say some kind of cylindrical, some kind of tube is deep in the liquid. Just think about liquid like water. Some kind of tube is deep in the liquid. Then if you do the liquid surface, so we can see some kind of what? So in this way, sorry. Then last I explained the direction of surface tension on the liquid and direction of surface tension on the solid. Then what happened? Then you can clearly see that what happened. It seemed like these liquid surfaces are somewhat. It seemed like these liquid surfaces are pulled in this direction. Then what's the direction of surface tension acting on the liquid surfaces? This way. But one direction of surface tension forces acting on the solid object. The direction of surface tension forces acting on the solid object will be this direction. T, this angle T. Am I correct? Angle of contact. This one, same as T. Then how can we find the resultant surface tension force now? Already explained this thing when the angle of contact is less than 90 degrees. Now tell me, when you consider this object deep in this liquid, what is the resultant surface tension force? What is the resultant surface tension force acting on this object? If I resolve this T into perpendicular components, T cos theta down, T sin theta away, all T sin theta components will be cancelled out. The resultant surface tension force acting on this solid is downward direction, T cos theta into the perimeter. If I say radius as simple R, capital R, 2 phi capital R into T cos theta. The resultant surface tension force acting on this object, resultant surface tension force acting on this object is 1. 2 phi R T cos theta. This is the word resultant surface tension force is acting vertical down direction. If I ask you what is the okay now okay then resultant surface tension force 2 phi R capital T cos theta. Now just think about the capillary rise. If you think that capillary rise, then we know that a liquid of height simple h rise in this capillary simple h. Then if I ask you what is the direction of surface tension forces acting on the liquid, direction of surface tension forces acting on this liquid will be something like this. The direction of surface tension forces acting on this liquid will be this direction. Okay, this angle is theta. Then my question is now, understand if there's a capillary rise in a liquid, it seems like someone has pulled that liquid along the capillary tube. What is the direction of surface tension forces acting on the liquid? What is the direction of surface tension forces acting on this liquid? This direction, upwards. So what is the resultant surface tension force acting on this liquid column? If I resolve it, T cos theta upward direction, T sin theta cancel out. Resultant surface tension force acting on this liquid column will be upward direction, that is T cos theta into 2 phi capital R. The perimeter. If you take it as a circular capital T. Then, in addition to resultant surface tension force acting on the liquid column, what is the other force acting on the liquid column? Weight, mg. Mg. If you consider equilibrium of liquid column, we can write down T upward force is resultant surface tension force. T cos theta into 2 phi capital R must be equal to mg. Now simple means mass. I can write down mass means volume into density. What is volume? If you think this liquid column has some kind of solid cylinder, volume means what? Cross-sectional area into height. Cross-sectional area is phi capital R square into height is the volume. Mass means volume into density rho g. T cos theta into 2 phi capital R. When you simplify this, you will obtain that. Again, same equation. H rho g equals 2T. H rho g equals 2T cos theta over capital R. I hope you guys understand. Right? Okay. Then that's the main idea behind this. Okay. Right. I have those things. Now put your another subtopic, liquid rise between two parallel plates. Next subtopic is liquid rise between two parallel plates. Liquid rise between two parallel plates. Liquid, same idea now. Now, how we derive this equation? Very similar manner. You want to derive the equation for liquid rise between two parallel plates. In this case, now in the liquid, if I dip two parallel plates, right now, in between these two parallel plates, what would happen? This liquid will be raised. Then let's say the height of the liquid column rise in between these two parallel plates. As simple as, and we can see that simple edge height of liquid column has rise in between these two parallel plates. If you consider the liquid column above the liquid surface, if you consider the liquid column above the liquid surface, This would be the liquid column above the liquid surface in between these two parallel plates. Right? So then this when you consider this liquid column, seems like some kind of a cuboid, right? If you carefully look at the liquid column this time, liquid column maintained in between these two parallel plates is like a cuboid volume. Then again, same idea. Now, when someone looking from this side, the wave would be appear this way. When someone looks from this side, the wave would be appear in this way. Then surface tension forces acting on the column will be T. Surface tension force acting on the column will be T. This angle is theta. This angle is theta. 2t cos theta. 2t cos theta. Right. What can you say about the circumference, if not the length of the solid which touches the liquid column? This length. Am I correct? This is the length of the solid which touches the liquid. Then let's say length of the parallel plate simple L. Then this is simple L, simple L. If I say simple D means gap between, simple D means gap between these two parallel plates. Simple D means gap between these two parallel plates. Then I can say that resultant surface tension force acting on this raised liquid column will be 2t cos theta into what? 2d plus L, right? Am I correct? 2d plus L. The thing is, understand now. Now I made a small mistake. It must be 2 The reason is because now only the solid surfaces would be the parallel plates. Always length. We always consider length of the solid which touches the liquid. Now there are only two parallel plates. So therefore, only we have to consider the total length of two parallel plates, L plus L, 2L. Because in this, there is no contact with solid. Because liquid in this region, there is no contact with solid. So therefore, just 2L. Just 2L. This is the total resultant surface tension force acting in upward direction. That must be equal to weight of the liquid column. So I can say that 4T. Okay, I can say that 4 TL cos theta must be equal to mg. Mass means volume into density. Now volume means how do you know the volume? L simple D into height simple h. LDH. LDH density rho g. 4TL cos theta. Am I correct? Okay, L cancel out. L cancel out. It's T cos theta. T cos theta 2L. My bad. T cos theta 2L. Then again, you'll obtain that H rho g equals 2T cos theta over simple D. The equation. Then I think that's surface tension. All theory parts will be covered. Now from this, all surface tension theory parts is covered. So therefore, please go through the theory again, and we'll do some questions. We'll do some questions. First of all, watch these recordings as far as possible. Okay.